Hello everybody, welcome to this video looking at the comparison test for convergence and divergence of series. So here the idea is that we're first with the series, we want to decide whether it converges or diverges. Then the idea is that we're going to compare it to something we already know and try to conclude based on that what happens. So let's see how it works. So there are two directions. So suppose we have two series, some of A and some of Bn, and they have positive terms. So positive terms is important for the comparison test. So two series with positive terms, and an is less than bn for every n. So there is a series with small terms, a series with large terms. So an is the small series, bn is the large series. Then what can we say? Okay, if the sum of bn converges, so if the sum of the large series converges, then also the sum of the small series converges. And vice versa, if the sum of the small series diverges, then also the sum of the large series has to diverge. Okay, so if the large series converges, then the small series converges. If the small series diverges, then the large series diverges. Which makes sense, and it's kind of like what we had for the integral test, right? We had also a comparison test in that setting, and everything was pretty much the same with sums swapped to integrals. Okay, so let's see, for instance, an example here. Does the sum of 5 over 2n squared plus 4n plus 3 converge or diverge? So notice that the terms are going to 0, so we can't use a divergence test. We can't use any of the tests we've used so far. It's very hard to integrate, though we could probably do it. But a way easier method is to use the comparison test. So let's notice that the thing we started with is less than. Remember, if we want to make a fraction larger, we can either make the top bigger or make the bottom smaller. So here we can make the bottom smaller by dropping the 4n plus 3. We just have 2n squared. We keep the most important term, right, which is the largest term, which is 2n squared. This becomes 5 over 2 times 1 over n squared. So we started off with our an is 5 over 2n squared plus 4n plus 3. And now our bn is 5 over 2 times 1 over n squared. We know the sum of 1 over n squared converges. So in particular, hence the sum of 5 over 2 times 1 over n squared converges. It's just multiplying by a constant. And the series we started with is smaller than that. So the sum that we started with also has to converge, right? We are smaller than a series. We already know how to converge, hence we converge. And I didn't mention, but here clearly the series have positive terms. Okay, so this is a pretty typical application of the comparison test, where smaller than a series we already know converges, or where larger than a series we already know diverges. Okay, but quite often, I mean, here it was a simple example coming up with the inequalities, but inequalities can be quite hard to come up with, especially if you have things happening on both the top and on the bottom. So there is another test called the limit comparison test. People tend to find taking limits easier than doing inequalities. So what does that say? Suppose we have two series with positive terms. So always in this section, we want series to have positive terms. Sum of an and sum of bn, they have positive terms. And let's suppose that when we look at an divided by bn, so we drop the sum, we just look at the individual terms. We do an divided by bn, we simplify, we take the limit. Let's suppose we get a finite positive number c. So it's important here that the c we get has to be strictly positive, so bigger than 0. It's not allowed to be 0. And also finite, so it's not allowed to be infinity. So it's strictly positive, bigger than 0, and also finite, so less than infinity. Then either both series converge or both series diverge, so they have the same behavior. So we can use one to conclude information about the other. So typically what we're going to do is we start with some complicated series. We want to decide if it converges or diverges. And then we try to pick out the most important points. Maybe if it's a fraction, we pick the biggest term on the top, the biggest term on the bottom. That's some other series. We check that they have the same behavior by checking that an over bn tends to a finite positive constant. And then if they do have the same behavior, then we can instead look at the simpler series to decide whether we have convergence or divergence. So let's see an example. So does the sum of 2n squared plus 3n over the square root of 5 plus n to the 5 converge or diverge? So if you're really confident with inequalities, you can also do this one with a comparison test, but maybe an easier way is to do the limit comparison test. So this is our one series. We have to come up with another series to compare it to. And the idea is that let's drop the smallest terms on the top and bottom and just pick out the most important terms. So let's come up with an as our starting series, or the terms in our starting series. Let's choose bn to be the largest term on the top, 2n squared, divided by the largest term on the bottom, which is the square root of n to the 5. If we simplify, we have 2n squared divided by n to the power of 5 over 2. It's going to become 2 over square root n. And then we want to check they have the same behavior, meaning that an over bn tends to a finite positive constant. So if we do that, we look at an over bn, we have an, which is the thing we started with. Rather than dividing by bn, since bn itself is a fraction, let's flip bn over and multiply. So rather than dividing by 2 over square root n, we multiply by square root of n divided by 2. We multiply this through, we are going to get 2n to the 5 over 2 from the 2n squared times square root of n, plus 3n to the 3 over 2. And then we want to take the limit of this, and it's going to depend on what an and bn are to see how we do this, but at least in this case, the leading term on the top is 2n to the 5 over 2, And the biggest term on the bottom is an n also to the 5/2 multiplied by 2. So this is actually going to tend to 2 divided by 2, which is 1. You could check this, for instance, by multiplying, by dividing through by n to the 5/2. So this tends to 1, and 1 is obviously a finite number and a positive number, strictly positive. So we can apply the limit comparison test. So rather than looking at the sum of an and trying to decide whether that converges, we can look at the sum of bn instead. And we know that sum of bn diverges, for instance, by the p-test. So the sum of 1/n to the p converges if p is strictly bigger than 1, diverges if p is less than or equal to 1. So here the p is a half, which is less than or equal to 1. This is a p series. It diverges since p is a half less than or equal to 1. Okay, so this was a pretty typical application of the limit comparison test. And maybe one last thing to mention in this section is using comparison to estimate remainders. So remember, we started talking about this in the previous section on integral test. But quite often, if you're using the integral test, maybe the remainder is hard to calculate. So one thing we can do as well is compare it to something which is simpler. So let's suppose we have two series, sum of an, sum of bn. Sum of an converges to s, sum of bn converges to t. They have positive terms, and an is always less than bn. So bn is the large series, sum of an is the small series. And then let's consider their partial sums. Sn are the partial sums of the small series, Tn are the partial sums of the large series. And let Rn and Tn be the corresponding remainders. So Rn is the remainder for sum of an, Tn is the remainder for sum of bn. Then you can check that always Rn is less than Tn. So here what we are saying is that if we have two series with positive terms, one is small, one is big, then the remainder for the small series is less than the remainder for the big series. Okay, makes sense? So how would we apply that? So to estimate the remainder for our small series, we can instead estimate the remainder for the large series. So here's a problem. If we use 100 terms to approximate the sum of 1/n cubed plus 1, how accurate is the remainder? So this is a pretty typical problem, or typical looking problem from the integral test section, right? The thing we're summing, sum of 1/n cubed plus 1, it comes from a function 1/x cubed plus 1. So we can apply the integral test, hopefully, to show that it converges. But then how do we estimate the error? So if we were to try to do that, we would have R100 is less than or equal to integral from 100 to infinity of our function. So remember this inequality back from the last section. But this integral is very tough to calculate. The integral of 1/x cubed plus 1, there isn't really a nice antiderivative. Maybe if you factorize and use partial fractions, you'll get there in the end, but this is very hard to integrate. But instead, we can compare our sum to something which is simpler. Right, rather than think about the sum of 1/n cubed plus 1, we can think about the largest series 1/n cubed, right? And why is it larger? Remember, if we make the bottom smaller, the terms become larger. So 1/n cubed plus 1 is less than 1/n cubed. So rather than estimate the remainder for the smaller series, we can instead estimate the remainder for the largest series, sum of 1/n cubed. And now that is something we've seen how to do, right? We use the inequality. The remainder is less than the integral from 100 to infinity of our function, except now we have the larger function 1/x cubed. This we can easily do, right? The antiderivative of x to the minus 3 is x to the minus 2 over 2 over minus 2. So minus 1 over 2x squared. We plug in a t, we plug in the 100, we subtract, and we let the limit as t goes to infinity, which we can actually calculate. Okay, so just to summarize, we talked about the comparison test, right? If the sum of the large series converges, then the sum of the small series converges. If the sum of the small series diverges, then the sum of the large series diverges, assuming we have series positive terms. Then we had the limit comparison test, which is a similar thing, but instead of having large and small, we have to check that an over bn tends to a finite positive number. And then at the very end, we said that if we want to estimate remainders, we can estimate the remainders for a larger series instead. Okay, thanks everyone. See you next time.